is a great skill to practice, incidentally, and Pete's pretty cagey about doing this, having to do this. Summarize something in just a short paragraph. It's really important. Just like the 2-minute description of your research project. And I knew that years ago, so I worked on a description of what I was doing in research in case Warren Buffett came by the office and wanted to invest money, right? Warren, he never came by, but I had this 1 or 2 minute statement about what I was doing that's aimed at a person who doesn't understand science. That's the tricky part. But you guys did a good job in writing. It's really to your credit. From last lecture, we talked about columns and sizes and shapes and missions for the columns, analytical versus preparative. We talked about pressure drop and the various contributors to pressure drop and how they contribute to the second power or the first power inversely or whatnot with the Cosenate-Karman equation. And that'll show up, or that idea will show up in a couple minutes about that. And that has to do with how you design a method. What are the parameters in which with which you can operate to do an efficient separation? And what you try to do is avoid surprises like huge pressure drops that can break the column down on you and cost $1,000 and that kind of thing. And then we talked about packing materials, silica mostly, with beads and solids and follicular beads. And remember that's mostly solid, but with a thin layer of permeable silica on the outside, so that there's actually material into and out of the silica matrix, but not deep into the bed. The fused core is a thicker layer than the follicular, and often can have 2 different size ranges of pores. Didn't talk too much about it. Large pores on the outside and narrower pores on the inside. And then briefly something about monoliths. All right, and that's more for you to keep your eye on as you keep going in chemistry and hear more about these things. As I said before, I don't know what the news is finally going to be on that. There's some promise to it, but there's not some promise to it. We talked a little bit about bonded phases and end capping, and I want to pick up there with a couple of other ideas because I've caught a couple of the statements led me to believe that you still need to know a little bit more about it. What we're doing is a condensation reaction on the surface of the particle. We're taking a chlorinated silane, and this is just a general one, but this is probably the most popular one. The most popular agent, though, has another R group up here. Usually these are 2 methyls, and this is a C18 group, and then a chloride. And this reacts with the OH to cut out HCl and leave a silicon-oxygen-silicon bond. And this one has 2 chlorines on it, and that'll sometimes produce these bridging structures like this. And then you see the C18, we don't show it extended, but in your mind's eye, it extends up like a long tail. And that's a very oily group, right? It's like diesel fuel, long alkane, and it has low polarity. It can be polarized because you can, depending on what you bring up close to it, you can make electrons move away or move toward. Not terrifically polarizable, but still pretty polarizable. Okay, and then in the second possibility, we can bring up trimethylsilane to do what we call end capping, which is, remember that this first step, for some of the best procedures here, the first step will only be about 50% effective in covering spaces. So only about half of the active sites will be bonded to this, what we call bonded phase. And the other sites are still there as OH sites. And they're very polar. Remember that silica just by itself is what we call a normal phase material. Highly polar, it attracts polar species. What we're trying to do here is to take the silica and use it as a foundation to build a reverse phase surface on, an oily phase on top. We have a lot of these polar groups left behind, however, so that we have oiliness up here, but polarity down here. And so some solutes can come down and interact. We get a mixed mode of interaction, which is not always good. It's not always bad, but it's not always good. So one of the things we can do to cover for the fact that we only have about 50% of this good oily stuff on the sites is add something that's small and can work its way down and react with the silicon, some of the remaining SiOH sites, maybe half of them, maybe 2/3 of them, something like that. In the finished product, there's still going to be SiOH bonds, but we hope to protect the world from them by having these other groups bonded. Now remember that 2 methyl groups on this silicon here will also help shield the surface hydroxides. Here we see the methyl group helping to shield this one so that adventitious molecules coming in may not be able to get down to that hydroxide very easily. They're kind of kept away from it. So there's this shield defense. All right. So this also shows you something about polymeric bonding. Here we have the species that is the most popular species, the C18, dimethyl C18 with chlorine. And then that bonds and leaves us with these long chains. And this is the idealized view. It doesn't show any remaining SiOHs. And this shows a polymeric silane, either 2 or 3 chlorines on this. And when you have more than one site, you can either go down and bridge 2 silicons, as I showed you before, or you might, it's going to be hard to bridge 3. What you can do is have another silicon come in and bond to a silicon that's in place before a bridge forms. And so you can have an extended 3-dimensional structure across the surface. That's a bulk phase. And that's going to have different properties than just this phase with the long tail sticking out. It's like an extra population, not 100%, not probably even 30%, but still an extra foamy kind of population here to do separations across. Here's a little picture of end capping. Now y'all got an idea what end capping involves, huh? Using a small molecule to cap the SiOH. And this shows how that works in there. And you can see this surface gets really strained sterically. These sites are, well, let's see, I don't know, several angstroms apart, maybe 4 angstroms apart, something like that. So you've got methyl groups that pretty well shield them. Let's talk about some popular reverse phases. Okay. Here's the classic, most popular octadecyl silane, C18, and also available in C8 and C4. Now, if you were to just make a guess about the oiliness of these reverse phases, which would be the most oily and which would be the least oily of this group of possible? Just take a guess. This would be the most oily, the long chain. This would be the least, C4. So what you find here is that C18 is the strongest reverse phase medium. It does the best separating. And C4 isn't nearly as selective as C18. It still does its own job. It does okay. And you make a choice between C18 and C8 and C4 based on the particular application. Let me say that most analytical laboratories get their instrument shipped with a C18 column because it has the most general applicability. A company may find that the C4 works better because they don't need to do as much separating, maybe only one compound they need to analyze regularly. And the C4 works fine with that, and it's maybe less expensive. Maybe. Okay, instead of having just carbon sticking out here, let's take and put a terminal nitrile group on the compound. And what do we know about nitriles? What are they like? You ever seen a nitrile walking down the street? That sounds like a song, doesn't it? And what do we have for electrons? No more extra electrons around here. Lewis theory, there's 8 electrons, but a pair of electrons there. So a pair of electrons sticking out from the stationary phase. So this is going to be a more polar reverse phase column. And this will select toward more polar solutes that move by. Acid base reaction, but you can have polarization occurring from these electrons. They can polarize other molecules near them. Here's another, actually there are 2 packings. I only had, since there's limited space, I showed you the F5 compound. And you can also remove all the fluorines if you want to, start with a benzene ring. And these compounds are a little more selective toward aromatic compounds. More selective. They are a little bit fragile. This compound in particular, there's enough electronegativity on these fluorines that they pull electrons in this way and create more positive centers here, which can be attacked by solvent, so that you find that these columns will degrade more quickly than the C18 columns. But again, they have a selectivity that you would go looking for if you had a particular problem with solvent. Okay, all right, the F5. You guys upstairs in Pete's lab use an F5 column.
Yep.
Down here is an amide phase, and this is pretty interesting because the amide group is not, in this particular description, not at the end of the molecule, but it's toward the middle of the long molecule. This is a C14, 15, 16, 17, 18 carbon compound, right? Oh, did I say that? 7? Yeah, 18 at least. 14, 15, and then carbon 16, 17, 18 carbon. And then an amide group in the middle of it. Now this amide group is not way at the end, but it's mostly, actually it's more toward the silicon, isn't it? It's called an embedded amide group. Now what do you suppose its properties are like? Now you have to understand that amide is a base. Oh, a base, so maybe we'll want to get protonated or something. So you might think it could attract more acidic compounds, maybe. But what else? What do you suppose the effect of the long chain sticking out is? To modify that behavior and give you a mixed, what we call a mixed mode of selection. Both oiliness and charge then are involved in this. And once again, this is a kind of a compound that you might look for if you had a particular separation that was not performing very well with the C18. Yeah. Polar embedded. There are some other mechanisms that you're going to want to know about, at least hear a little bit about. Ion exchange is a very important method. And we have anion exchange material here and cation exchange here. Notice this is a quaternary ammonium salt, right? And so the positive charge here will draw up anions to associate with it. So if you have a collection of ions, anions and cations, the cations would move right by this stationary phase pretty much unimpeded, so they'd come through the column real fast. The anions, did I say that right? Cations would come through pretty much unimpeded. But the anions will be attracted to the positive charge and cling around. What they'll do is displace a chloride and then hang out with this stationary phase for a while. Slang, huh? Now here's a cation exchange stationary phase. Notice these are not 18 carbons long, they're 4 carbons. And this is a sulfonic acid group, so this is a strong cation exchanger. And again, this is going to attract positively charged ions, but negatively charged ions will move on by. And this will, as positive charged ions come here, they'll displace water of H+. And also carboxylates can be used. Carboxylates are weaker cation exchange resins. Remember the pKa's of these are bigger than of these. Sulfonic acids are pretty strong acids, pKa of 1 or something like that. pKa of 4 for carboxylates, just for your reference. Here's a picture I pulled out. A tryptic digest of bovine serum albumin, BSA, which is kind of a tour de force material for doing peptide investigations, meaning that if you want to show off the instrument, you can do this. Anybody know what trypsin does? It digests BSA. It looks for, along the chain of the peptide, it looks for lysines and arginines. And it will hydrolyze those points. So what you get from a long peptide chain that's been treated with trypsin is a collection of small chains of amino acids. And those small chains then can be separated on a column. Sorry this is so busy, but this shows you 2 different runs. But I think you can see that here a 20-minute chromatogram with the cation exchange, you're getting all these particles from the original bovine serum albumin out, and you're looking for particular components here. Just if you can pass this stream on to a mass spectrometer, you can probably get a better idea of what each of these components are. They're oligopeptides or smaller things. Probably dipeptides on the smaller side here. Oligos up in here. Okay, so this would be of use, I suppose, if you're studying metabolism. Let's say, since it's bovine serum, just fancifully, we have a mutant cow. We want to see if we can figure out what's wrong with the cow. So we take the serum albumin, and let's say we find a peak out here that's double the size. If we can track this down and identify where that peptide lies in the chain with the help of our friends in biochemistry, then we have a way to understand more about that mutant cow. All right, I'm sorry, but you get the idea. I hope you do. Size exclusion. I believe we're going to have a lecture sometime between now and the end of the course dealing with the aspects of size exclusion. And just briefly what this is particles that have pores of different ranges of sizes, some big and some small. You put in a mixture of materials, we could even use some of the peptides that we had before, proteins of different sizes, and they come in and separate out all the particles try to get into, the proteins try to get into the particle as best they can by diffusion, right? They go from where they are to where there aren't so many of them. They're loners. And what we find is that the little proteins can dig down into the pores much more deeply than the big proteins. And after the whole mess of proteins goes by and the concentration up higher in the column declines, diffusion outward occurs, right? Now, if you're a small protein and you've gone deep inside this path to get way down into the particle, it's going to take you longer to get back out again, isn't it? So in a column like this, the small proteins move through the column much more slowly than the big proteins. They bounce off, they can't get inside, so they come pretty much with the solvent. Depending on the stationary phase material you have and how big the pores are and how their distribution is. Okay, you don't want chemical interactions necessarily because they can mess things up in the order. So you want this to be kind of inert, and you want this to play, you want the universe to play with the diffusion in and out of the pores. Whoops, went too far. So this is a size exclusion chromatogram. And this is done with a Phenomenex Yera column, which is bonded silica, and has a range of pore sizes, and you can see the effect of this. These are the proteins that are coming through. Can you see the molecular weights? Peak number 1 is from 699,000 molecular weight protein, and peak number 2 is 300,000, and then 150,000, 14,000, 17,000. And then I don't know what that is, but again, the large molecular weights come out first. The small molecular weights come out last. And you can see this is pretty cool. These are almost on the baseline. These are nice, clean separations. Now, if you're doing a study on one of these proteins and you don't want the others around, you can track one of the elution peaks in a little vessel and then do with it what you want to do. So it's a good method of separation that way. More than just analyzing how much, you can actually track the stuff. This is fancifully, it involves cyclodextrins, which are like polysaccharides. And you can see they come in different ring sizes. They're studded with OH groups. And you can do a couple of different kinds of derivatization. You can derivatize with chlorines to get the cyclodextrin to stick down on the silica particle. And you can derivatize on the top with optically active stationary phase. The shape of the cyclodextrin is kind of like a cup. And this is not very wide, 10 angstroms. but it can fit a molecule down into it. And the way the molecule fits depends on the chirality of the decorations on the cup at the top. So if you have a right-handed collection, a collection of right-handed molecules bonded to the cyclodextrin facing up, okay, that means you're going to retain the right-handed solute that goes by it. While the left says, I'm not comfortable here, this is completely wrong, I'm going to move on, which comes out the detector early. You follow? So what you do is you make an optically active phase which will attract or not attract the different stereoisomers that are coming out, R and S. And the example I have here should be close to you because you're a lot of graduate students. You're going to be taking this stuff when you take your prelim oral, right? Prozac. And this shows you the R and S isomers of Prozac. Where's the optically active center here? Tell me if I'm cold or warm. Fine.
Cold.
My grandkids are doing this over the weekend. We were hunting Easter eggs, and I would go and, cold, no, you're freezing. You turn around, now you're warm. It's a place where there are 4 different species coming, so, right there. That's not that, and it's not that, and there's an H there, it's not shown. So that's the optical center. So there's an R and an S one here. And this would not be a big deal except that the R one of these, and actually I'm not sure which is the R and which is the S. It wasn't given in the boilerplate head. But the R one, the S one works fine to settle you down, right? Settle your nerves before they. The R one though stimulates arrhythmias in the heart. Well, that's not good, right? So if you are selling Prozac, you want only one of the isomers in the product you're selling. You don't want the one that's going to do damage. You'll have lawsuits. You'll hurt people. You don't want to do that. So if you can't find a way to synthesize only the R or only the S isomer here, and that's where Tom Hoy and the organic chemists come in because they learn more and more about how to do the specific stereochemical synthesis. If you synthesize both of them, you have to use some preparative chromatography method to separate them before you put them into a pill so that you have them in the right form. Right? This is a very important use of preparative LC in industry. Extremely important. Purifying drugs. It's also a reason that drugs are so expensive. I know it's the way they get old. I mean, it's just terrifying. A couple thousand a year in drugs. And the reason for that is that you have to go to a lot of heroic steps, with these newer products because they're very hard to synthesize, very complex molecules. All right, now I'm not going to belabor this. It will be on the web. I'm going to give that to him to put on. But I do want to point out one of the advantages that HPLC has over gas chromatography. And that sounds odd and out of left field. Sorry. In gas chromatography, the separating ability of a column really depends on the nature of the column material, but not of the mobile phase. If you go around and look at gas chromatographs around the university here, I'll bet 99.5% of them are connected to helium gas. Fine gas, wonderful. A little bit pricey now, but the mobile phase is always helium. So how is it that how do you change the separating power of the GC experiment?
Temperature.
Yeah, program temperature, right. And if that doesn't do it, change so you can take some close peaks at the beginning and run them cooler and then ramp up to get the later ones to move down in, right, to save yourself time. So temperature is your variable there. If that doesn't work, then you go to something like a cyanide group connected to the end of the long column and you play with the column. But you see that most of the chemistry there is independent of helium. Now in HPLC, you have the ability to change the stationary phase and the mobile phase and the temperature. Remember, we showed the temperature changes the viscosity. So just an easy question, which is probably the more facile, adaptable method?
GC.
GC is a very good method as long as the materials you're working with are volatile. All right. And if they're not volatile, then you've got some real trouble. Brian, are you a GC fan?
I am.
Okay, sorry.
That's all right.
It's a one in every crowd. Okay, so we've got normal phase, reverse phase, ion exchange, SEC. I don't have Tyrol done in this table. This is Pete's table. And this shows you about the stationary phases and what they're like, and then the mobile phases that are appropriate for them, okay, that are usable with them. So I want you to take a look at this and learn about this, all right? And it should be very easy for you to pick them. Now a little bit about solvent delivery systems. We have about 20 minutes. I'm going to talk about main components. Again, these pretty pictures are all going to be on the web, so just sort of watch and you'll see a lot of things that are familiar and some things that aren't too familiar. But these are the points that I'll try to get most of. Here's a color picture of what was illustrated in black and white last time. Solvent, pump, injector. We have just a valve before. This now suggests some sort of automatic injector, and everybody uses those now. Column, detector, computer, do computer up here, and then the fractions that are separated. There's nothing unusual about this. We're going to look pretty closely at the pump today, and something about, which doesn't show up in here, mixers, and also de-aerators. So for good pumps, we need high pressure, because remember it's high performance LC, and it used to be called high pressure liquid chromatography, right? And then as Pete so often says, and then for a while it was called high price chromatography. And believe me, it's still high price chromatography. We need a consistent flow rate. The flow rate can't be pulsed. Every pump that is a reciprocating pump, like the ones you're going to be seeing here with a piston that moves in and out, has the ability to create a pulse. And what we have to do is dampen the pulses by using both multiple pumps and by using pulse dampeners. We have to have a wide range of flow rates, as high as maybe 5 mils per minute for analytical work, and maybe a couple hundred mils per minute for preparative work. So we need to have, the pumps used for the preparative are a quite different variety than the ones we use for the analytical. We're going to focus on the analytical. They need to be chemically resistant. We don't want them dissolving in the solvent, right? And they have to be resistant to abrasion, to scratching, unless we're very careful getting particles out of the solvent stream. They also should be low maintenance. And one of the things, if you work in HPLC as a graduate student, you're going to learn how to maintain pumps, change seals and all that cool stuff. You'll win the Golden Wrench Award. So here, scale limits. These are maximum pressures. Again, don't copy this down, and you'll find it. And maximum flow rates. And here, if I were to write an exam, I'd want to put on a question like this, because this emphasizes what you saw last time we were together with the Closity-Karman equation. If you know particle size, column length, and diameter, and solvent viscosity, could you calculate the maximum flow rate for a pressure not to exceed 400 bar? This 400 bar pressure for this kind of work is an important one. You try to plan not to exceed that. Now, there's a new class of instrumentation called ultra high, or even bigger. And of course, that means that those close Prozac peaks are going to get a little bit harder to separate when you have to use a less efficient column. Just keep that in mind. There's a lot of good stuff that the chromatographers can contribute to the use of these different kinds of instruments. Here's a reciprocating pump. Very nice picture, I think. Shows you heavy stainless steel construction. There's an inlet and an outlet. This goes to the solvent reservoir and a degasser. And and this goes to the outlet, ultimately to the sample valve, and then to the column. And a couple of very simple ball valves, check valves in here to control the flow. The plunger runs in and out, driven by a cam, which you'll see in just a minute. The plunger itself is made up typically of sapphire, aluminum oxide. The valve seats here are typically also made of sapphire. Sapphire is very resistant to chemical attack and very resistant to physical abrasion. Right? These seals are very tight because remember, you have to push so hard, you're pushing maybe 400 atmospheres of pressure here in some experiments. Think about the job that the seals around this piston have to do. Now, if you have some particles coming in with the liquid, and those particles get around this piston, unless this is an extremely hard material here, it's going to abrade the piston and cause some channels for leaking, and you're going to get leaking of solvent out here. It won't cooperate at higher pressures. Okay. Another material commonly used now is silicon carbide, another incredibly hard material. Okay, so there are seals in this thing. This moves, as I said, this is a reciprocating piston here. They're fairly inexpensive. Yeah, well, inexpensive is a relative term, isn't it? The first one of these I bought at Gustavus in 1980 was in a unit about this size and cost about as much as an automobile, okay? So relatively inexpensive. Obviously high pressures. It does produce pressure pulses, which we try to control. And of course the seals wear out, but that's why I created graduate students, so that we could have them change the seals. If you haven't seen check valves before, it's a trivial idea, but this is what they look like. And incidentally, springs are not necessary in here. So when this is open, that means fluid is flowing in from below and the ball can float up and the fluid around the ball and can move on. So if this is at the bottom and this connects to the reservoir of solvent, as we pull the piston out, fluid comes up around the ball. And then when we push the piston in, the fluid pushes down on the ball and stops flowing. Okay, not so difficult. Remember, there's another check valve up on the top, above it immediately, not immediately, but up in the ceiling. And when we push on that to close this one up, that pushes the ball up on the one up above. So the balls work together to direct the flow through and over to the column. So when we push, it goes up. When we pull, that one closes, but this one opens up and it refills the piston chamber, okay? This is a diaphragm valve, and this shows you, this is your view of a cam. Does everybody know about cams? They're like eccentric wheels. If this were a perfect circle, and we turned a motor on this line here, we turned the motor here and turned a perfect circle, nothing would happen. But since this is eccentric, as we turn the motor and push it this way, the wider part of the circle comes and pushes this inward. Follow that? And then when the shorter side comes up, then a spring will push the plunger back. So we push and then spring back, push and then spring back, and the eccentric shape here allows us to do that. Okay. The virtues of this, no chemical contact between the pusher and the flow of material here. The pressure pulses tend to be lower in this kind of design. There are limits to the maximum pressure because of this design, but the flow rates can be somewhat higher than before. You clear on this? This makes sense? Instead of having this long piston push in and out, we're just moving a diaphragm to push. This is a syringe pump. These are beautifully free of pressure changes. It's a nice linear motion. And you can drive this with a motor and a screw and just drive this, fill up the a syringe and then push the needle in with the motor, and that pushes it into the stationary phase. There's a limit there because you have to refill it. So if you get 10 mils of solvent through that, you've got to stop the experiment, refill it, and then start it again. But for short-term experiments, it works very, very well, and it's not subject to pressure glitches. It's very precise, too. Let's see, I can show you this, I think. Also, well, we might as well use this picture. It shows up in the next one, too. Here we have a binary pump. Now here we've got the solvent coming in, and our pump has 2 different motors and 2 chambers. Why do you suppose you want to do this? This is like the pump that I showed you before, the piston. Let's say that you only have this one here, and this one is not here. When you push this in, you've got a check valve that keeps it from going through the solvent valve, so it only goes in one direction. And then when you pull this down, what happens? You no longer push out, do you? So your experiment, which is pushing the solvent through the stationary phase, is interrupted by the withdrawal of the piston. So you separate for a while and then you stop, and separate for a while and then you stop. So it's like a quicker syringe kind of pump. So what Agilent did, I believe they were among the first to do this, is to put a second one in here so that when this one is driving, this one is filling. And then when this one goes to refill, you're still pushing on this side to push the liquid through. So it's not interrupted. It's not interrupted. Very clever idea. It also puts in a second motor, right, and costs 2 cars instead of 1 car. Not that they do things like that deliberately, but people need that. So 2 pump heads. Okay, now this shows that 2 pump head with the addition of a damper. Now this is going to be a metal diaphragm, and the purpose of this is that the thing will flex a little bit, so if there's a sudden pressure change, the flexing will keep the pressure change from transferring on down the line to the column. It's a little bit like putting a capacitor in an electronic circuit. The capacitor can take care of AC sudden events like that and dampen the signal through the electronic circuit. So there's a damper that can be used in here, and the usual arrangement of check valves and whatnot. But in addition here, we've got solvent bottles that come through something called a deaerator. And this is a vacuum chamber, not a perfect vacuum, no such thing, but something can be easily provided by a fairly small air pump. The lines flow through Teflon tubes inside this, and the gases that are dissolved in the solvents that come through will permeate the Teflon, but the solvent won't. Okay, so since this is low pressure on the outside, the gas pressure in the solvent is higher, and what happens? Henry's law, right? The fugacity increases and the gas comes out of the mobile phase. So this lowers the amount of gas in the mobile phase. I said a little bit about this last time. We have to avoid embolisms, and what can happen here is that you can mix 2 different solvents together, for example, methanol or acetonitrile and water, and if the organic material has a lot of air in it, the water will cause the air to evacuate and form bubbles. Those bubbles are bad. I don't think I showed you in the check valve, but bubbles in a check valve will make them stutter, and that produces a change in the flow and interferes. Bringing in solvents that will provide different solubilities for gas, and that's what this evacuator is about. Low pressure with a vacuum, and then selecting the right mixture from the valve, and then pressing it outward. Okay. Oh yeah, and while we're going on here, you can probably see that actually this first chamber serves as a pre-mixer for the final. There's mixing in this chamber, so you actually get some benefit from extra mixing in this. Here's a degasser, a commercial one. You can see the Teflon tubes that are in here, and this is evacuated. The whole unit's evacuated. You don't have to use those things, but it sure is convenient. There's an alternative. You can take and sparge, it's called, the solvents with helium. Okay? And helium is not very soluble in solvents of any kind. And since it's not, when you have a lot of it in the solvent, it'll drive out the other gases, and you'll be left with just a small amount of helium, and you won't have the trouble with the bends. Okay? So this shows, again, this shows about everything except this shows mixing. This is a mixing chamber, and then a final mixer up in here. So there's a mixer and a damper and whatnot. All right, so this is a more complicated instrument. This is a cutaway view of a mixer. And I was amazed when I first saw these things up close. They're quite extraordinary. They're very carefully machined, and little pathways are cut into a block, right? And the pathways here come, this is the source of the liquid coming out and breaking down into channels, finer channels, and then taking this circuitous route. These turns and twists will make the liquid tumble and mix it that way. So you pull it apart, mix it, and then reunite it down in here. And this can have a very small volume. The jet weaver, I believe, has only about 75 microliters, something like that.
There are smaller ones also.
Yeah.
36, the one we have.
Wow, it's
Yeah.
amazing, yeah. Tiny, tiny volumes here.
Yeah.
Yeah. I can't understand this one. It's Pete's fault. It looks like it's three-dimensional, but it's. I can understand Star Wars, but not this mixer. A little bit about performance tests, and then we're done. These are tests that we run to see if everything's working right. In industry, they have to be done pretty frequently because the stakes can be very high. You have to make sure that you're not looking at bad data, because you have a product you're trying to sell to somebody, you have to guarantee that product to somebody. So you have to be very careful about this. So flow rate, how do you measure that? Old-fashioned way, a stopwatch, an analytical balance, and a vessel that, okay, will not allow much evaporation because it takes a while. What you do is you turn the instrument on to a particular flow rate, take the output from the detector, put it inside your vessel. Oh yeah, weigh it before you put it in there. And then turn on the stopwatch and count for 30 seconds, 50 seconds, whatever it takes. And then weigh the amount of liquid that's transferred. It works just fine. Oh yeah, and so, and if you weigh it then, and you know the composition of fluid, you can calculate from the density the volume that's passed. Typically, 1 or 2 per, about 1% for 20 microliters uncertainty. Real good old-fashioned method of determining flow rate. Okay, linearity and dwell. We haven't talked a lot about gradient elution, but I bet you have the idea. In gradient elution, you change the composition of the solvent on the fly. You start out with, in almost all cases here, except for the technique highlight, you start out with a high polarity solvent and you add lower polarity solvent to it and ramp up the composition of the low polarity stuff, okay? So that's what this is about. So this is the signal. What we do here is we use, let's see, water as our initial solvent, and then our second solvent is 2% acetone and water. And we monitor, now acetone has a ketone group, so it's a chromophore, and it shows up at, I don't know, maybe this is 270, something like that, around where ketones usually show up. And it's a nice big signal. So what we do is we start out the experiment, and we tell it to start pumping B into our solvent A. And there's a little delay here. What's this delay from? It's from the distance from the mixer to the column, right? Oh yeah, but we take the column out for this. Sorry, I didn't say it. And we put a 0 volume union in there. So we're just measuring the time and centered, in other words, through the system, right? We're looking at the rate of the pumping, so we don't care about the count. We're just taking the output and sending it to the detector. After the delay from the mixer, which is a short time, we can calculate the volume of that because we know what the flow rate is, and we know the time, so we can calculate the volume. Then we start having more acetone added to it. And look at that nice sloping line there. And then up here, we no longer add any more acetone. We're up to 100% acetone solution. And then we let it relax back down. Okay, this has to be right. It has to agree with the settings that you have on the instrument. If it doesn't, then one of your pumps is going too fast or too slow. So this is a routine quality check. You follow me? So you have two pumps, one of which pumps A solvent, the other B solvent. They join together, merge and mix, and then go through to the detector. And to check the speeds of those pumps, you do a sloping line like this. Very straightforward. And we can do this with steps on the solvent. 10% steps up here, 5% here, 10% again here. So we can see the accuracy of the preset steps in the method. Now this is easy to do. You tell the computer what to do. You say, all right, computer, you're going to start with only solvent A, and then after 2 minutes, you're going to step up to 10% solvent B, and then after another 2 minutes, 10% solvent, 20% solvent B, and so forth. Step up. What do you suppose you want? You want nice sharp steps, and you also want flat steps. Okay. See, are these perfectly flat? What do you think that might suggest? What would you look for? Anything? I mean, maybe they're supposed to be perfectly flat. Maybe it was, but it came from Agile, I believe. It looks like it might be a leaky seal on one of these pumps, maybe. I don't know, but that's where I would start looking for trouble. Ideally, these would be perfectly flat and perfectly straight. We're just about out of time. We would want to measure the reproducibility of the retention time. Okay, and this is from some consulting work that I did with a company down in St. Peter that makes drug mixtures for veterinary medicine, and they have to do quality assurance tests all the time. So this is checking out the instrument. And now there's a lot of words in here. The peak areas were reproducible. You want to see if the integration is working right and the detector is working right. About 2 parts per thousand relative standard deviation, 0.2% for the peak areas. For 5 replicate injections, that's performing just fine. Okay, nice and quantitative. And let's see, mean of 2.05 parts per thousand for 9 sets of 5 replicates for one of the compounds, and 6 sets of 5 replicates for the other compound. Clearly, the injection system is working. The retention times are also highly reproducible. Now, this is a little complicated, I apologize for it. 9 sets of 5 replicates, okay? So we take 5 replicates of a sample, and we do that 9 times, all right? And we were doing that with making a working curve. The mean retention time was 3.0616 minutes with a standard deviation of 35 milliminutes. That's milliminutes, you never heard that before. It's science, it's good. So 0.035 plus or minus 1 standard deviation, 0.035% relative standard deviation. And then for 6 sets of 5 replicates, the retention time was 4.4193 standard deviation. Okay, so I think you can see that this is highly reproducible. The retention times are reproducible, which means that if you're working on a product, you can confidently say that the peak that comes out at this time is what it ought to be, and it's not some errant peak. Okay, well that's it. Again, send me emails with with a summary and with questions, and I'll deal with it as best I can. And I've enjoyed this, and you reacted better today than you did last time, so that's good. I crave laughter. I don't know what's wrong with me. So it's been great. Good luck with your futures here. And, you know, it's going to work out here. The course is going to work out. So you need to have some faith in the ability to see the